Okay. Shoot. Let's hope I have enough battery. Pencil is like running out of battery. Okay. So today I know like he didn't really have lecture like these past Friday and Monday, right? So I'm sort of going off on like the videos, his past videos. So like the ones in the folder are like his previous year videos. So okay. So I think today instead of going deep into ideals, I think that's like way too much. So I think I'm gonna go, how do I say it? Just we're gonna go over examples of tons of examples of ideals, yeah. So recall for groups. Um, well, right. We have that G quotient H set of cosets, right? And this becomes a group when H is normal. So we say, what about rings, right? So given R, ring R, and like I is something, right? We want to say like R mod I is a ring. Yeah. So what's this I? Like what's the equivalent of like, normal subgroup in like a ring, sort of, right? So it turns out it's an ideal. So let N be additive subgroup of a ring R satisfying AN is a subset of N, and B is a subset of, oh, yeah, N for all A, B, and R. So this thing, it's, how do I say it? So it might look confusing at first, but just think of it like, think of N like a magnet. Yeah. It sucks in everything. It sucks in anything multiplied by elements in R. So it sucks in anything multiplied by elements in R. Right. So I mean, a quick example is like, we know subgroups of Z, right? So before I continue, does everyone understand what I mean by additive subgroup? What do I mean by additive subgroup? Anyone? Yeah. So remember, a ring has two operations, right? So when they say subgroup, they have to tell you under which operation. So additive just means it's a subgroup under the operation plus, right? So Z plus times. So we already know like NZ is ideal of Z, right? So of course you have to prove it's an additive subgroup, but we already know from group theory, NZ is a subgroup of Z, right? Under the binary operation plus. So you just need to check this is true, right? So basically to check this, you need to say like, given like basically given to check this, you need to check, given n in n, an is in n for all a and r, right? So given a and z, is it true that a times some element here, so some element in here looks like n times z, right? Is this in n times z? Well, yes, because it's commutative, right? So I could swap it. And now this thing is in z, so this is in n times z. Yeah? And you could check, since this is commutative, right? This is the same as by associativity. It's just this. This is in Z, so this is in NZ. Yeah. so this, so NZ is an ideal. Is everyone clear so far? Is everything clear? Okay. So you can see, think of it like a magnet. So what if R is ring of unity, right? So it's a ring with one, and I is ideal with one. What can you say? So again, it must suck in everything in R, right? So this must be true for all A and R. In particular, if I take the element 1, A times 1, which is A, has to be an I. Everyone agree? Because it's a magnet, right? If 1 is in there, then but this is for all A and R, right? That means every element in my ring has to be in my ideal. So you see, in this case, I is just R. Yeah. So this is called one of the trivial ideals, you know, like I mean, like it's once you so example, right? If I have a field, is a field, what ideals can there be? Yeah. So you could always have the zero ideal, right? The just the set zero. Clearly, this is an ideal because I mean the zero, I mean the identity subgroup, right? And anything times zero is zero. So it certainly sucks in everything because anything times it is just itself. So, but what else, right? So if not, right, then I has some element u, right? Not u not equal to zero, right? But then what do you know about fields? Like like what's the property of a field? Like what do you know about the element u? It has an inverse, right? But in particular, I must suck in everything, right? So if u is an I, then u inverse times u, which is 1, is an I, right? So I'm taking, again, AI must be an I for all A and R. So I'm taking u inverse as my A and u as my element in I. Yeah. But then if 1 is in there from, from this thing right here, I must be just the whole ring. Yeah. So you see, fields are, in particular, ideals are not very interesting, right? You either have zero or the whole ring. So hopefully you all see difference, right? So people ask like, what's the difference between subring and a ideal, right? Well, subrings, there's many subrings. Sorry, let's just say it's R, right? I mean, let me just say F, right? So take F to equal the real numbers, right? The real numbers is a field. So the only ideals, as we stated, is 0 and itself. But there are certainly like many other subrings here, right? Like you could take subrings given by Z, Q, right? And whatever you want to think of, right? So I mean, so don't subrings are sort of different from like ideals, right? Subrings don't have this suck in property, right? Um, or call it magnet property. Okay. Everyone clear so far? Yes or no? Okay. So now again, let's check its let n be ideal of R, right? Then the claim is R quotient n is a ring, right? So this is the set of additive cosets, right? So cosets under the addition operation. So how do I define multiplication here? Well, it's pretty clear. We define it like this, right? Right. This is how you multiply in this ring, and this is how you add in the ring, right? So addition's obvious. It's just, a plus b plus n. Yeah. So first question, why is this a ring? So why is this I mean, I'm not going to go over it all, but the one part is a bit easy to check, right? Why is R mod n and abelian group under plus, right? You need to check it's a ring, right? So you have to show it's an abelian group under this thing, right? So before that, why is it a group? So recall n is a subgroup of is an additive subgroup of R, right? So n is a subgroup of R, but what do you know about rings? Like what is it? Like R is a ring. So you know by definition it is a abelian group, right? Under plus. Does everyone agree? And what do you know about abelian groups? All subgroups are normal, right? Remember? Like if G is a group and H is a subgroup, normal means this, right? Abelian is stronger because it means this. Yeah. So if you're abelian, you're always normal. Yeah. Because this just says GH1 is H2G, right? You could swap the H and G, but the H might change. Here just means you can just always swap. Yeah. So if you remember, like, is everyone clear on this? So you see N is a normal subgroup because by definition of a ring, it's an abelian group under plus. So the fact that it's a group is clear, and it's abelian based on how we defined it, right? Like this is just adding in the ring. And I know R is an abelian group under plus, so this is B plus A plus N, which is B plus N, A plus N by definition. Yeah? Everyone clear on this? Okay. So let's continue. So with this, you have your isomorphism theorems, right? I'm just gonna go over one of it today. Probably the most important one. Fundamental homomorphism theorem. The book really words it like in a really awkward way, but R to R prime be ring homomorphism with kernel N. Yeah, then phi of R is a ring. The map and the map mu from R quotient N to phi of, so you would have to check this is well defined, right? So the fact that it's well defined is, because of the kernel, n is the kernel. So phi of r is isomorphism given by mu of x plus n equals phi of x. This looks really complicated, but really just know this. If phi is a ring homomorphism, this is basically saying r mod the kernel of phi is, because phi of r is just the image of phi, right? So it's isomorphic to image of phi. Yeah. So before this, I'm not gonna prove the whole thing, right? But before this, what do I mean by it's isomorphic as rings, right? So you would have to check that image of phi, i.e., like phi of r is a ring. That's one thing you have to check, right? But another thing is, why is this, right? In order for this to be a ring, if we go back, right, r quotient n, we're taking n to be an ideal, right? So you would have to check that, for this to make sense, kernel of phi better be an ideal. Yeah. So one thing to check is so to check it's an ideal, right? You need to check kernel of phi is additive subgroup, right? Under plus, right? And two, right? You have to check the ideal property, right? So in other words, let me just say if R is in R and X is in kernel phi, you need to check that Rx is in kernel phi. Yeah. So let's work with definitions, right? So today we're just going to practice the definition of ideal. Yeah. So let's check property 2, right? So suppose X is in kernel phi and R is in R, right? What does it mean for X to be in the kernel of phi? Yeah, so phi of X is 0, right? So I need to show want to show, right? Rx is in kernel phi. So I need to show phi of Rx is 0. Well, phi we by assumption is a ring homomorphism, right? So this is phi of R, phi of X, right? Again, this is multiplication in R prime, right? And I know this is 0 because this thing's 0. And anything times 0 is 0. Yeah. So this shows again, and then show the other way, right? So again, show, and then similarly, X times R is in kernel phi, right? But let me just say another way. Yeah. Because if the ring's commutative, you don't need to check the other way, right? Because Rx is XR if if um if the ring's commutative. But in any case, right? And the fact that it's a subgroup is under plus, right? Is basically the group homomorphism property, right? If x y is in kernel phi, then x plus y is in kernel phi, right? Because phi of x plus y is phi of x plus phi of y, which is 0 plus 0, which is 0. Yeah. So again, plus is a binary operation here. Everyone clear on this? Yes. No. Mostly. So not fully. I mean, I guess I didn't prove everything, right? But the proof is long. That's why. I mean, I'm sure the professor will do it. But I'm just bringing up like the important key points. So okay. So let's work with R mod I, right? So example. So R is Z of X. So the polynomials with coefficients in Z, right? And I is the ideal generated by X. So this is X f of X such that f of X is an R. Right, so why is I an ideal? Well, this is quite clear, right? Because given g of x in R, right? And x f and like x times, let's take some arbitrary element, x times f1 of x in I, right? Because every element in I looks like this, x times a function, right? I need to check that this is an element of I, right? And it certainly is because this is just, I mean, this is multiplication, right? So I could just, it's commutative. So this thing, I mean, if this is in Z of X, this is in Z of X, it's a ring. So this, both of these are in Z of X, or if you like, in R. So you see like it sucks in anything. And it's certainly an ideal, I mean, it's a subgroup under plus because, I mean, it's certainly closed, right? Like x f of x plus x g of x is x times f of x plus g of x, right? This, since both are in z of x, this is in z of x, or if you like, R. So this thing is in I, right? Everyone convinced that this set right here is an ideal. Okay, well, the question is just, let's work on describe R quotient I, right? So let's work with quotients. So if I asked you, right, what's Z mod 4Z, right? Like you would, how would you describe this? Like, how do you know it's elements 0, 1, 2, 3? Well, because here it's whatever you quotient by, you're basically saying 4Z is 0, right? If you think about it, like 4Z is the identity. The identity is 0 in this case, right? So you're basically saying any multiple of 4 is 0 in this group or in this ring. Yeah? Everyone sort of get that? So here we're sort of saying I is 0, right? So if I is 0, what is I? Can anyone describe what I is for me? Like these are polynomials such that what? They have no what? Like, do they have a linear term, quadratic term, constant term? Like what do they not have? Yeah, no constant term, right? So you see, polynomials without a constant term is 0. So in this ring, right? So the idea is like given f of x is a n x to the n plus a1x plus a naught, right? If a naught is 0, this thing at f of x is an I. Do you agree? Because if a naught is 0, I could factor out x and make it a n x to the n minus 1 plus a1, right? And now this is an element of I, right? It's x times something in R. Is everyone clear on this? So you see that so anything without constant term is 0. That reduces our ring a lot, right? Anything without constant term is 0, right? So, and more frank and quite frankly, like what you're gonna think is obviously like um any two polynomials with same constant term What can you tell me about those? For example, let's just make it up, just so you all see. So let's say they have the same constant term 10. I don't know, 5x to the 100 plus x to the 34 plus 10. What do you know about these two polynomials? So I'm asking you, are they equal? Basically. How about that? I'll give you a hint. Are they equal in the quotient? Yeah. So if I give this as f, this is g, right? F minus g is what? 5x to the 100 plus x to the 34 plus 2x squared plus 3x. Is this element in I? Uh, yeah, that's what we're trying to figure out right now. I'm basically telling you what we're trying. Yeah, like we're basically describing it right now for you, right? So I'm saying like it's certainly like a subset, right? So I'm saying like right here, right? Like if like 2x squared plus x, this is an element in R mod I, right? But I'm saying this is 0 because this element's in I, right? So yeah. So kind of like this, right? 4 plus 4z, right? So you could think of this as like the class of 4. This is 0 in z quotient for z, right? This element, because it belongs to 4z. so we're sort of describing like what elements are 0 here and what elements are not. So we know anything without constant term is 0, right? And anything with the same constant term, well, so if I subtract it, is this element in I? Is 5x to the 100 plus 34x, x to the 34 plus 2x squared plus 3x. Is that an element of I? Yes or no? Yeah, right? Because I could factor out the x and then it's x times something, right? So you see, put two polynomials, but if it's an I, it's 0, right? So f minus g is 0. So you see, polynomials with the same constant term are the same element, right? In R mod I. So we might as well just take the representative to be the constant term, right? Like this is just equal to 10, right? Like in R mod I, right? Because this thing is an I. So it's in 0. It's just 0, right? So hopefully you could just see like here the representatives are just all the integers. 0 plus I, 1 plus I, 2 plus I. And then, -1 plus I. So on and so forth, right? Everyone clear on this? Yes or no? You will be taking quotients a lot in the future, so please tell me, like, if you don't understand, or you will be lost. So, yes, so whenever you quotient out by something, right, you're basically saying like that thing is 0. So, another example would be maybe like let's practice like x squared, right? So let's do the same thing, but take the ideal generated by like x squared. z of x, right? So this is, again, the set of x squared times f of x, such that f of x is in z of x. Yeah? So, I mean, it's kind of similar to what we write here, right? Here, this is 4z is the set of 4 times z such that z is in z, right? Kind of analogous. Yeah? So here, right? What is 0? Anything, any square term is, I mean, anything where you have an x squared in it, you could factor on x squared, is just 0, right? So if I gave you a degree like 5x to the 100 plus 10x cubed plus 2x plus 1, this thing is 0. Agree? Because I could write this as x squared times 5x to the 98 plus 10x, right? And this is an element, so we could call this I if you like. Yeah, this is an I. Does everyone agree on this? Oh, okay, ignore. Okay, so does everyone agree that all quadratic terms and higher go away? Yeah, we can just kill off all quadratic terms, right, and higher, right? Because if I had like 5x to the 1 million plus 10x squared plus 1, anything squared and above just go away because they are in I, right? Yeah, so you see the elements here. So elements in this ring are the classes are classes, right? The representatives are basically all the ax plus b, right? Plus I, where a, b is in z, right? I mean, it just runs through all these linear terms. Does everyone understand quotients so far? Like, I mean, here I'm just taking an arbitrary element in z of x and saying what can I reduce, right? Kind of like here, if you take like 105, right? What can I reduce? Well, I know any element in 4z is 0, right? So what can I do? Well, I know 100 is in 4z, right? So I could take out 100 and still get the same element, right? And similarly, right, I could take out yeah, exactly, because like here, right, for example, just take this one. You could always, if it's quadratic or higher, you could just factor out x squared, right? And then you have 5x to the, I'm not going to write what this is, minus 2 plus 10, right? And now this element is an I, right? So it's 0. Exactly. I mean, if it's q of x, it's the exact same. I mean, if it was q of x, the answer would just be this, right? I mean, right? I mean, like the coefficient. I mean, it just changes the where your coefficients can live, but it doesn't change the fact that you could get rid of all x squared terms, right? So, does everyone understand ideals and like quotients now a bit more? hopefully you see the analogy. I just want you all to see the analogy to like this thing, right? Like it's completely the same thing. Like you've been doing this like the whole time. It's just we're working with a different ring now. Here it's the exact same thing, right? If I told you like 104 plus 1, right, you would say that this is the same as 1, right? Because I could kill off 104 because it's an element of 4z, right? It's the exact same idea. Sorry. Yeah. Why is it an ideal? Just check it. So take g of x in z of x, right? I need to check and an element. So an arbitrary element looks like x squared times, I don't know, let's call it f1 of x in I. So this is like some arbitrary element in I, right? Then I need to show g of x times x squared times f1 of x is in I, but this is just x squared times g of x times f1 of x. And this thing is in z of x, right? Because each of them are in z of x. So this is an I. So you just check the properties. Yeah. Please, is there any more confusion? So I'm telling you, you have to know this, because if you don't know this, you will not understand field theory when we get to it. So, so this is the crux of like field theory, which we will go over soon. So please tell me you understand like taking quotients. Basically, whatever you quotient by is 0. So you could always get rid of it in a sense. Yes or no? Can I continue? Uh, I guess you are all a bit confused because like the professor didn't really talk about this. Yeah, it is. So this is the same as the element 1. So this is 1 in z adjoint x quotient x squared z adjoint x. Yeah. Okay, good. So let's continue. So another way to think of this is you could define a map from R to Z, right? If R is Z adjoint X, right? Or I'll just write Z adjoint X. If you're not comfortable with what I just did, then this certainly makes sense, right? And then I send an x to the n to a naught. Yeah, so again, let's take I to be the ideal generated by x. So it's x times f of x such that f of x. So it's the previous example. But instead of x squared, I did like x. So one way to show this is, what's the kernel here? The kernel here is what? The kernel are those that go to 0, right? So those that go to 0 just means you have 0 constant term, right? So it's polynomials without constant term, which is just I, right? This was what we did before, right here, right? It's stuff without constants. Everyone agree? And certainly the image of phi is z, right? It's certainly surjective because, I mean, 1 goes to 1, 2 goes to 2. I mean, the polynomial, the constant polynomials go to the constants in Z, right? So, I mean, so this is, so phi is surjective, i.e. phi is surjective. Yeah, so by first isom or fundamental homomorphism theorem, which I went over, right? Fundamental homomorphism theorem. So this is another way to describe R mod I, right? So Z of X quotient I is isomorphic to Z, right? Because I was the kernel of phi, and this is the image of phi, right? So I'm using this thing, right? So if phi is a map from R to R prime, then R quotient kernel is isomorphic to image, right? So I'm telling you, we showed that the kernel is I and the image is Z. So you see that these two rings are isomorphic. And the reason for that is what I did here, right? Is isomorphic to Z because you could take any integer as a representative, right? So this is like by construction, right? So this is more explicit to so this is something you should know how to do. But certainly you could also use the fundamental homomorphism theorem to just show what R mod I is. Whichever way you like, whichever way you prefer. Is everyone clear on this? Yes? No? So, yeah, okay. Good thing I didn't go. I know the professor went into like prime ideals and maximal ideals and stuff, but I felt like just since ideal is like new for everyone, I think it's better to just do more ideal, just simple ideal questions, so we all understand. So let's take if IJ ideals. So next time I'll go over like the maximum and prime stuff. Is I plus j, which is the set of I plus j, where I is in I, j is in j. Is this ideal? And is I intersect j an ideal? So again, let's practice with, so again, I'm doing these just so we practice definition, yeah? So let's check, right? I plus j is a subgroup under addition, right? So what do I need to check? I need to check that it's closed, right? Well, given two elements, x, y, and I plus j, right? I need to show x plus y is in I plus j, right? Well, I can write, since x is in I plus j, I can write x as I1 plus j1, y as I2 plus j2. Then x plus y is I1 plus j1 plus I2 plus j2. But remember, R is a, sorry, IJ ideals of ring R. That's kind of implied, but since R is a ring, it's an abelian group under plus, right? So it's abelian, so I could swap. Okay, now this is an IY because we're given that I is an ideal, right? So I, by definition, is an additive subgroup. It's a subgroup under plus, so it's closed under addition. So if I take two elements in I and I add it, it remains in I, right? And same thing here. This is in J because J is an ideal, right? So we're using the fact that they are ideals now. And from here, so this is I, so this is an I plus J, right? And then I'll leave you to check the other group properties, yeah, for practice. I don't want to do it all. So now the more important thing is checking the 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 magnet property, right? So let R be an R, right? I need let X be an I plus J. I want to show that Rx is an I plus J, right? That's the magnet property, right? And I'll leave it to you to do the other way, the X times R. But here, right, let's check it, right? Since X is an I plus J, X is I1 plus J1. Agree? So R times X is RI1. I skipped a step. So this is distributive property, right? We are in a ring. So we have the distributive property. Okay, now this is an I because I is an ideal, right? We're given I is an ideal. So if I take an element I1 and then multiply by any element R, it remains an I, right? Because I is an ideal. It's a magnet. So same thing here. This is in J, sorry, right? Because J is an ideal. So this is an I plus J. Yeah. So this is an ideal. Yeah. Everyone clear on this? So, like, hopefully by now you understand the definition. Everyone clear? Yes? No? Okay, so let's just do this and call it a day. Let's do the I intersect J and call it a day. So I intersect J, right? So let X be an I, intersect J, X, Y, right? Then I need to show that X plus is closed under, it's an additive subgroup, right? So X plus Y is an I intersect J. Yeah. But this is clear because if X is if X is in I intersect J, X is in I, X is in J, right? And this means Y is in I, Y is in J, right? That's what it means to be in the intersection. Y is in both I and J, and X is in both I and J. But this means X plus Y is in I, right? Because if X is in I, Y is in I, X plus Y is in I because I ideal, right? It's a subgroup, it's additive subgroup. And similarly, X plus Y is in J because J is an ideal. Right, so since I'm in both I and J, X plus Y is in I intersect J by definition. Yeah, I'm in the intersection if and only if I'm in both of them, right? And again, I'll let you check the others. So let's check the magnet property because that's the new thing. So given R and R, X and I intersect J, I need to check that Rx is in I intersect J, right? So again, I know Rx, right? X is an I intersect J, so I could view it as an element in I. Now this is an I because I is an ideal, so it has the magnet property. But also, since it's in the intersection, this is in J as well, right? So this is also in J because J is an ideal. It also has the magnet property. So that means Rx is in both I and J. So Rx is in I intersect J. Yeah, so you can check that this is an ideal. So where to go? So this is also an ideal. Yeah. So I'm just going over definitions so we are all comfortable with it. So next time we could go into stuff more in detail, more harder stuff. So I just want you all today to get used to definition. Just get the magnet thing in your head. Magnets and quotients. Okay. If that's all, I will see you all Thursday then.